All right, we're in chapter 5. This is the last chapter that we cover in this class, and it's a shorter chapter than any of the chapters we've actually covered so far. There's only 5 sections, but it is jam-packed with really important content. In this section, we're going to look at something that we haven't really explored yet, and it's going to lead us into a really important concept in calculus, which is the integral. The integral is what you're going to spend probably the majority of Calculus 2 working with, but we introduce the concept at the end of Calculus 1. We're not going to even start using the word integral until section 5.2, and we're not going to be able to do much with it until about section 5.3. But what we're going to do here is talk about the problem that motivates this definition of the integral. And we start with the concept of area. Since geometry, in fact, long before high school geometry, as far back as elementary school, you've talked about areas of two-dimensional figures, two-dimensional shapes. Usually starting with the area of a rectangle or a square, because those have the easiest area formulas. Moving up to areas of triangles and trapezoids and various different figures. Now, from geometry, we know that area formulas of polygons are relatively easy to come up with. Polygons have a nice property in that all of their edges are straight. And from the experience that you should have in geometry by the time you get to a class like this, you should know that it's not terribly difficult to find area formulas for those types of shapes. What's difficult, though, is finding area formulas for shapes that have curved sides. With the exception of the circle, in geometry, it's unlikely that you would have dealt with the area formulas of any other curved shapes, unless I'm forgetting something. So in this section, we're going to explore that concept. But a little bit more specifically, we're not just looking at curved shapes. What we're doing is we're finding the area between a curve in the Cartesian plane, so a curve that's given by a function, specifically the area between that curve and the x-axis. So you can see in this little image right here, we have some function y equals f of x that's been graphed, and we're specifying a specific interval in the domain of that function, the interval a, b, so it kind of cuts out a little region there. And the region S is trapped between the part of the function that lies on that interval a, b and the x-axis. We want to come up with a way of determining the area of this region S here, okay? Our technique for doing that, as has been the case in all the way back in the beginning of this course, when we talked about the tangent line problem, we're going to start with an approximation. And this is the common theme throughout calculus. We want to solve a problem that is resistant to the techniques that we've covered prior to calculus, and our approach to solving it is using a limiting process. We start by approximating a solution to our problem, and then recognizing that if we can apply a limit to it in a specific way, the limit will take that approximation and turn it into an exact answer. So here's how we do that. We're going to start with this example, which is going to carry us through about half of this section. We're going to be dealing with just this one example kind of over and over again. We would like to approximate the area under the parabola y equals x squared over the interval 0, 1. And you can see here, this is what that region would look like. This is the parabola y equals x squared. Here you see the interval from 0 to 1 on the x-axis. And trapped between that curve and the x-axis on that interval is this region S. Now, I don't have an area formula ready to go to compute shapes that look like this. It looks kind of like a triangle, but it's not a triangle. That's not a straight side. So one way that could produce a good approximation, which we are not going to use, is you could join the points 0, 0, and 1, 1 by a straight line, which would give you a triangle if you took it together with these other two sides, and then compute the area of that triangle. Feels like that would give a good area approximation. But we're going to use a different approach, which will be really useful in other functions that we encounter later. We're going to use rectangles. So the process looks like this. We are specifically going to just use 4 approximating rectangles for this example, and then we'll use more later. What I'm going to do is start by taking the interval from 0 to 1 and subdividing it into 4 equally lengthed subintervals. So that would be the interval from 0 to 1/4, the interval from 1/4 to 1/2, from 1/2 to 3/4, and from 3/4 to 1. You see how that's 4 equally sized subintervals that we've split our initial interval up into. And then what that does is it creates what we're going to call a partition of the original region S. So if I had some way of finding the areas S1, S2, S3, and S4, the areas of each of these smaller regions, adding them up would give me exactly the area of S, the original region. But that doesn't help a whole lot because I still don't know how to find the area of any one of these as shown, because they're kind of odd looking shapes. So instead what I'm going to do is approximate the area of each one of these subregions using a rectangle. And the way that I do that, for this first example, I'm going to take the right endpoint of each of these subintervals. So that would be 1/4 for the first interval, 1/2 for the second interval, 3/4 for the third interval, and 1 for the fourth interval. Those are the right endpoints of those corresponding intervals. And I'm going to look at the point on the curve y equals x squared corresponding to each of those right endpoints. So here, I'll draw them in here, 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 and here. Those are the 4 points corresponding to those right endpoints. And then what I'm going to do is draw a horizontal line from each of those points that I just put on my curve, moving to the left, and stopping when I get to the left endpoint of that subinterval. So here, 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 here. And then that is going to determine 4 rectangles. Notice each of these rectangles, its upper right corner is hitting the curve y equals f of x because I used those right endpoints. The area of each one of those rectangles is going to be really easy to determine. So the area of this figure, this region right here, is approximately the sum of the areas of these rectangles. What is the area of each of these rectangles? Well, a rectangle has an area of length times width. The length of the base of this first rectangle is 1/4. What is the height of that rectangle? Well, the height of that rectangle is determined by the function itself, because it would correspond to the y coordinate of this point right here, which is 1/4 squared, because it's the function y equals x squared. So 1/4 times 1/4 squared plus the area of this second rectangle. The base is still 1/4, but now the height of this rectangle would be 1/2 squared, plus the base of the next rectangle, still 1/4, and its height is equal to 3/4 squared. Okay, and then I have this final rectangle, still has a base of 1/4. Each of these correspond to the width of these individual subintervals, which we intentionally made of equal size, times 1 squared. Okay, that's all arithmetic. If you do the work to figure out what that equals, you should end up with 15/32, or as a decimal, 0.46875. Okay, now obviously that's not the actual area of the region S, because this was used as an approximation. And I can say a little bit more. Based on the picture I'm looking at here, I could even say that it is an overestimate. I know that because if you look at the rectangles compared to the actual region that I'm trying to find, whose area I'm trying to find, each rectangle goes above the corresponding sub-region that it's approximating. So this rectangle is giving me too much area, that part that's above the curve. And this rectangle is also giving me too much area, all this stuff. We have excess in each rectangle, so that's going to result in an overestimate. Okay? What if I approached this slightly differently? what if these approximating rectangles were not determined using the right endpoints of these intervals, but what if instead I used the left endpoints of these intervals? So if you look at these rectangles, each rectangle has its upper left corner corresponding to a point on the curve. Its upper left corner is touching a point on the actual curve. That's because I'm using the left endpoint of each interval to determine the heights of these rectangles. So let's find the area using that instead. Once again, the width of each subinterval is going to be 1/4. And what is the left endpoint of the first subinterval? It's 0. So that becomes 0 squared. Now that would obviously give me an area of 0, which is why you don't see a rectangle there, but we're still including a term for that for the sake of completeness. My next rectangle is going to have a base of 1/4 and a height of 1/4 squared plus 1/4 times 1/2 squared. That would be the height of this third rectangle plus 1/4 times 3/4 squared. That would be the height of this final rectangle right here. Plugging that into a calculator or doing it by hand, however you prefer, that's going to give me 7/32, which is equal to, as a decimal, 0.21875. Okay? So I've approximated this area using two different rectangular approximation methods. That's what these are called, rectangular approximation methods. And in one case, we had what was easily determined to be an overestimate to the correct area. Down here, I have what I can also easily determine to be an underestimate of the correct area, because if you look, each rectangle is missing some more area above it that would correspond to each of these subregions. So this rectangle is underestimating the area of region S2 up there, for example, and so on and so forth. This is an underestimate. So what that tells me is that the true area of this region S, which I'm calling A, is somewhere between 0.21875 and 0.46875. Okay? So I'm going to use that as my answer. My approximation is that the area is in between there somewhere. It's some value in there. Now, the process that we just used incorporated 4 rectangles in each method, whether I used right endpoints or left endpoints. Even though this first rectangle actually had an area of 0, I'm still going to think of it as a rectangle. So I'm thinking of this as being 4 rectangles, not just the 3 that we see. There was no reason that I had to use just 4. What if I used more than that? Well, we're going to look at that in just a second. But before we do, I want to talk about some notation. So I'm kind of discussing in these paragraphs the stuff that we're talking about here, how we came up with the areas of each of those rectangles. Now, I used 2 methods. I used right endpoints in one method and left endpoints in the other. So if I use right endpoints to approximate my area under the curve, I'm going to use the notation Rn. R for right endpoints Rn. And the n here is equal to the number of rectangles that I was using. Similarly, if I use left endpoints, Ln is the notation I'm going to use for that approximate area. So what that means is that in the previous example, because we used 4 rectangles in each approximation method, we computed R4 and L4. So let me go back and use that notation. This was R4 and this was L4 off the page there. L4 down there, okay? What if I increase the number of rectangles that I'm using to approximate this area? What if I were to use 8 rectangles instead of 4? Well, what's that going to look like? Here we have the left endpoint and right endpoint methods that we used for the same exact curve, but with 8 rectangles instead of 4. Now, the width of each of my rectangles, or the base, I should say, is going to be 1/8 because I have smaller intervals. If I'm going to use 8 rectangles, then I'm chopping the interval from 0 to 1 up into more pieces, which means each subinterval is going to have a smaller overall length. And then plugging in the left endpoints, I'm seeing that these rectangles appear to be doing a better job of filling up that region under the curve than the 4 rectangles did. Okay? And that's just kind of eyeballing it. So comparing this to this, there is kind of a lot of empty space that's being missed when I did 4 rectangles. And it kind of looks like I'm making up for some of that by choosing more rectangles here. There's still missing space. But overall, it kind of looks like the net amount of missing space there is less than what we had here. Similarly, for right endpoints, we're still overestimating the area there, but the amount of excess in each rectangle, the amount that goes above the curve, seems to be overall a little less than what we saw here. There was a lot of excess when I used a small number of rectangles. So my guess is that the approximation to our area under the curve is going to be improved by using twice as many rectangles as we did in our first example. I'm not going to compute that by hand because it's going to be a really messy calculation, but the calculation itself is simple. It's the sum of 8 products in each case. The products corresponding to the areas of each one of these rectangles. So I'm going to just use the book's answer, because this is right out of the book, to say what the answer would have been if we worked it out. The left endpoint method, L8, is going to come out to this number, 0.2734375. Right endpoint is going to give me an approximate area of 0.3984375. Compare that to what we got here, okay? The amount of space between these two numbers is larger than the amount of space between these two numbers. What that means is that my area, I've got a tighter approximation on the area by choosing more rectangles. So naturally the question should be coming to mind, will the area under the curve continue being better and better approximated if I choose more and more rectangles using either of these methods? And the answer is yes. Rather than do this by hand, which would take a very long time because the calculations get very, very tedious for many, many rectangles, let's let a computer do the work for us. More specifically, let your book do the work for us, which use the computer. In this little printout, this little table here, n is going to correspond to the number of rectangles that we're using in either of these methods. So 10 rectangles, 20 rectangles, all the way down to 1,000 rectangles, which you would definitely not be able to do by hand. That would be impractical. But a computer has no problem doing that. In using each of these, when we run a program to compute the approximated areas in each of these cases, here's what we end up seeing. The left endpoint method is giving us approximations that are going towards this number, 0.3328335. The right endpoints are kind of coming down to this number, 0.3338335. This is a much, much tighter interval than what we saw up here. You might even be able to guess what these numbers are both independently approaching, something that's in between them. We're going to figure out what that is when we find the exact area under the curve in a little bit. But you can see that the more rectangles you choose by using this method, the better our approximation to the area becomes. And on the next page, I have a picture to help illustrate that because visually it's a lot easier to see. Here is my right endpoint method using 3 different computations. One has n rectangles, one has n equals 10 rectangles, one has n equals 30 rectangles, one has n equals 50 rectangles. There's 50 rectangles crammed in here. All 3 of these values were found in the table on the previous page, and these were the areas that we were getting as approximations. But just the picture themselves, you can see that by the time we get to 50 rectangles, it's actually really hard to see that each rectangle has a little bit of excess, because the picture that we're looking at looks very, very, very close to what the actual region S was looking like. Similar with the left endpoint method. Remember, the left endpoint method leaves little gaps between our curve and the rectangles, but those gaps are almost impossible to see once you include enough rectangles under that curve. Okay, so this is leading towards a really important definition here. It appears that as the number of rectangles increases, our accuracy increases. So if we were to apply a limit somehow, it would make sense that we would want the number of rectangles to go to infinity. And that, in fact, gives us an exact area if we do that. If we take the number of rectangles, which we're denoting by n, and let n go to infinity, then the sum of the areas of these rectangles will go to the exact area of that region under the curve. And this is how we're going to denote that. A, the true area under the curve on the interval 0, 1, is equal to the limit as n goes to infinity of Rn, and that's also equal to the limit as n goes to infinity of Ln. Remember, Rn is an overestimate in this case. It's not in every function, but in this case it is. It's an underestimate in this case, but the two numbers appear to be approaching each other. What happens when you take the limit as n goes to infinity is these two numbers squeeze down to one exact number, and that's what this limit is. So now what we want to do is compute the exact area under the curve y equals x squared over this interval. Now, how are we supposed to do that? Well, let's think about this for a moment. What would the sum of, let's just say, n rectangles look like? Well, if I were to do that, let's think about our interval for a moment. This is my x-axis. I'm only going to look at the x-axis for now. Let's suppose we wanted to find those rectangles over the interval from 0 to 1. If I take the length of if I take this interval and I chop it up into n subintervals, what would this next endpoint be? Well, the length of this interval is 1. 1 minus 0 has a total length of 1, and I'm dividing that into n equal pieces, which would give me 1 over n for that value. Next would be 2 over n, and then 3 over n. And this would continue until I got to n minus 1 over n, and then n over n, which is equal to 1. Okay, so that's where those subintervals are going to come from. Each one has a length of 1 over n. Now, how do I find the exact area under this curve? Well, we've talked about two methods. We can use right endpoints or left endpoints, and I'm going to choose to use right endpoints in my computation because the math comes out just a tad easier when I do that. But let's think about this. What will the area of this first rectangle be here? Using this right endpoint of 1, so I'm going to say my area is approximately, let's do this. Rn, I'm going to call it Rn to use the correct notation. Rn is going to equal the length of this subinterval, the base of that rectangle, which is 1 over n, times the height of this rectangle, but the height is determined by that right endpoint. I plug it into my function, which is y equals x squared, and that determines the height. 1 over n squared. Plus the height of this next rectangle. What's that going to be? Well, the base is still the same, 1 over n, but the height is going to be 2 over n squared. Okay? Plus the area of this next rectangle, which is still going to have a base of 1 over n, but the height is going to be 3 over n squared. And notice that this is going to continue until I get to this last rectangle, whose height is going to be determined by, whose base is still going to be 1 over n, but whose height is going to be this right endpoint plugged into my function, 1 squared. But let's try to keep things consistent here. Let's call that n over n, just so there's a kind of an apparent pattern here. N over n squared. Okay? Now I'm going to write this slightly differently. So first of all, notice that I have a 1 over n in each factor, which can be factored out. But then if I were to square my numerator and denominator in each one of these cases, I'm going to have an n squared in the denominator of each one of these as well. I can factor another 1 over n squared out, giving me 1 over n cubed here. What's left after that? 1 squared plus 2 squared plus 3 squared plus, and this is going to go all the way out until I get to n squared. Okay? Now, this guy right here, this sum of the first n squares, you may have at one point in time learned a what we call a closed form formula for this. So off to the side, I'm going to write this. 1 squared plus 2 squared plus 3 squared plus ... plus n squared, interestingly enough, is equal to n over n plus 1 times 2n plus 1 over 6. Okay? Put this example on pause for a minute. I want to verify this. So let's look at the sum of the first 3 squares. Okay, let me actually flip this over. What if I was just doing 1 squared plus 2 squared plus 3 squared? That would be equal to 1 plus 4 plus 9, which is equal to 14. Okay? Now, according to this closed form formula, that should be equal to n, which in our case on the back of the page is 3. I'm letting n equal 3. So 3 times 3 plus 1 times 2 times 3 plus 1 over 6. What is that? 3 times 3 plus 1 times 2 times 3 plus 1 over 6. This is equal to 3 times 4 times 7 over 6. Let's simplify. Divide by 3 to get a 2 here. Divide by 2 to get a 2 here. I'm left with 2 times 7, which is 14. Same thing. So we verified it for the case where n is equal to 3. If you wanted to prove that this formula works regardless of what you choose for n, you could prove it using induction. Induction is something you should have covered back in pre-calculus or college algebra. I think it's occasionally skipped at that level, but that's how you would prove a formula like this. And in section 5.2, we're going to introduce more formulas similar to this one, which we'll need when we're doing more work with this kind of concept in that section. But all that is to say is that I can use this formula to take this sum of n terms and convert it into a nice compact expression. So this is going to look like 1 over n cubed times this guy, n times n plus 1 times 2n plus 1 over 6. And then I can do a little bit of simplification here. I don't know why I put that as a subscript. 3 should be up there. I can cancel one of those n's with that n right there and write this as n plus 1 times 2n plus 1 over 6 n squared. Just combining everything into 1 there. Okay. All right, hold on one second. Okay. All right. Now, for the purpose of what I'm going to do in a little bit, I'm gonna write this guy slightly differently. So what I'm going to do, actually, I probably shouldn't even have done that. I can pull a 1/6 out of this, and I can write this as n plus 1 over n times 2n plus 1 over n. Okay, notice the n times n is n squared times the 6. That gives me the entire denominator. And then the numerators would multiply out to this as well. Let's simplify this a tad more. I can write this as 1/6 times, do the division here, n divided by n is 1 plus 1 over n. Here, 2n over n is equal to 2 plus 1 over n. Okay, so that was a lot of algebra simplifying, but the point of this was to figure out a formula that would give me my right endpoint approximation. Now this formula is interesting because I can now use any number of rectangles that I want, and rather than add up a total of n terms, I can plug it directly into this formula, and that's going to give me the entire approximation that I'm looking for. If you want, you can verify that with the table that we had. Plug a 10 in for n, for example, and see if you get the value that was shown there. What was that? For my right endpoint method, 0.35875. You should get that if you plug that right into this formula. What I need, though, is a limit. So the actual area under this curve is equal to the limit as n goes to infinity of Rn, or the limit as n goes to infinity of the expression that I just found, 1/6 times 1 plus 1 over n times 2 plus 1 over n. Now, if I were to take this limit into each factor of this product, it's only going to really do anything with these 1 over n's. And we know that the limit as n goes to infinity of 1 over n is equal to 0. These two terms are going to shrink to 0. And so I get 1/6 times 1 plus 0, so 1, times 2 plus 0, or 2. That's 1/6 times 2, or 1/3. So it turns out that the exact area under that parabola y equals x squared over the interval 0 to 1 is exactly equal to 1/3. And that's supported by the approximations that we got. Again, these two values were the best approximations we came up with, and 1/3 is equal to 0.3 repeating. Notice how close each of these values are to 0.3 repeating. That kind of confirms that we're getting a correct answer here. So we'll do more with this starting in part 2.